Hello again, B-Sides. Now, from our Breaking Ground track, Henry Reed and Emily Rexer will present static detection of novel malware using transfer learning with deep neural networks. Stay tuned.
Hello, we're very excited to speak at B-Sides Las Vegas. We're going to be talking about the static detection of novel malware using transfer learning and deep neural networks. My name is Emily Rexer, and I am responsible for a lot of the machine learning on this project.
My name is Henry Reed. I'm responsible for the data collection and infrastructure, as well as the project direction of this project. Others involved in the research include Nick Cohen, our senior cybersecurity project leader, who has helped us with some of his expertise, as well as Doug Woodward, who is our senior data scientist. And a lot of the code that we still use today has been written by Angela Tchaikovsky, our cybersecurity intern. So, the problem. Advanced adversaries develop custom malware that bypasses antivirus. When I say advanced adversary, this doesn't have to be a nation state. This could be a cyber criminal group, or it could just be a group of people who have the capability who can write custom malware. It is important for us as a community, an open source community, to research and develop new anti-malware techniques to improve cyber capabilities against that malware. Even if we lack the funding and the capability of a large antivirus corporation, developing those techniques helps the general community gain new skill sets and gain new capabilities that can then maybe be used in commercial, more sophisticated tooling. So it's important to keep researching this topic. Our approach was to base our work on the Intel and Microsoft machine learning approach, where they converted executables into images. Then they used those images with deep learning models to categorize malware as malicious or benign. Or categorize executables as malicious or benign. This method allows for predictive classification, meaning that malware that hasn't been seen before could still be detected. It's a form of static detection where no code execution occurs, and it's much easier to develop than something like a heuristic detection method where code will be run. For some preliminary statistics to get you guys interested, for x86-32 malware on Windows, I have 96.542% accuracy in detecting malware that has not been seen before. The intent of these charts is to act as an introduction to the research, as well as a tutorial to recreate the research should you decide to do so. We'll begin with our background, then we'll move on to our methodology, including dataset collection, dataset pre-processing, our models and experiments. Then we'll look at the evaluation discussion and finish up with feature work and the Q&A. So, ordinary malware detection is done mostly in two different ways: signature detection and heuristic. Signature detection is pattern matching of raw bytes with known bytes that come from malicious samples. If you ever use Yara rules, that's exactly how it works. It just matches things that it sees within the binary itself. Heuristic detection is a form of, essentially you run the malware, and if or you run a binary, and if the binary does malicious things, you categorize it as malicious. The third method, which is new and up and coming, is using commercial tooling. We have two examples of it, but it's not very common. For example, the FireEye Malware Guard uses raw bytes in both deep learning and non-deep learning approaches to identify malware. They explicitly state, and I quote, "Machine learning allows for detecting and stopping new malware faster than conventional signature-based approaches." Sentinel-1 is also another example. Current industry standard machine learning methods generally take text data off of a binary, similarly to ordinary signature detection, and then they use it in combination with a machine learning model. This requires a step called feature engineering, which is a time-consuming process, and then in the end you get a model that can tell you whether something is malicious or not with a percentage confidence. We are not doing that. Instead, we're using images and an image recognition model. I'm going to pass it off to Em, who will talk about this in more detail.
So I'm first going to talk you guys through an introduction to the broad machine learning workflow. So this is a flowchart. We're running from left to right here. So we first start with data acquisition. For us, that's collecting malware and benignware. Then we move on to data pre-processing, which again for us would be converting to images. And then we move into this sort of cyclic model experiments phase, where we train and evaluate a bunch of different models to try to get like the most accurate model. Once we're done with that, we take the most accurate model and we push it into model deployment. But currently, we're still in the model experiments phase. So now I'm going to talk a little more on the specifics of the model. So we're using neural nets in this project, which is just a system of connected nodes where the connections are modeled as weights. In this image, you can see that the leftmost layer is the input layer, and that's where we're going to feed in our images. In the middle, you have this hidden layer, which is sort of this like black box ML magic where everything goes on. And then you have an output layer on the right, and that is where our model will say either malicious or benign. And we're using neural nets because they can model very complex functions and they can take in images. But some problems with neural nets is that they require very large labeled data sets, and they're very computationally expensive to create, partially because of these large data sets. Another thing to note is that model creation is non-deterministic, which means that even if you feed in the exact same set of inputs, you're not always going to get the exact same model. So in order to try to counter some of these potential problems, we're going to introduce transfer learning. And transfer learning is just taking an existing neural net, pre-trained neural net, and retraining and adding some layers on top of it to fit it to a new data set. And so this image on the top here, you can see that that's the original neural net that we're transfer learning with. And then on the bottom, you can see that we've added a couple layers on top, and then we've retrained it in order to perform a new task. And so advantages to using transfer learning is that it requires a lot less labeled data than just like training a neural net from scratch. It's also a lot faster to train, partially because it requires less data. And you can also take advantage of neural nets that perform similar tasks. So in our case, that would be image recognition. Disadvantages to using transfer learning, though, is that the model you eventually create will not be as well fitted to the data as just training a neural net from scratch, because you aren't retraining the entire model. You're just retraining some added layers on top. So here's an example of how we feed an image into a neural net. Again, we're moving from left to right here. So we've got our image 3 by 3, so 9 pixels. We flatten that out from top to bottom, left to right. And then with each pixel, we convert that into a number from 0 to 1 based on its range of colors. So for us, it'd be from white to black, 0 to 1. And then you take each of these numbers and you turn them into nodes, and then feed that through the neural net. So now that we have our model, we need a way to evaluate which model is doing the best. And so these are called metrics, and they're based off of these 4 rectangles in this chart. So we have true positive, false negative, and true negative. And the metric we're going to look mostly at here is accuracy. And accuracy is just the ratio of all correct predictions to all predictions. So that'd be true positive and true negative over everything. And here we're aiming for 100%. I'm now going to pass it back to Henry so he can talk about inspiration and data collection and preprocessing.
So we base our work off of a paper called Stamina, Scalable Deep Learning Approach for Malware Classification, written by Intel and Microsoft. There are 2 goals in this paper. One is the malware classification problem, where knowing that something is malicious, what family of malware does it belong to? And then the second problem is detecting malware that you haven't seen before, meaning I don't know what this is it malicious or benign? That's the same problem that we're trying to solve. The approach is that, as we described. You convert a binary to an image, then you transfer a deep learning model on that binary image. We found a few issues. First, the suggested image conversion process negatively impacts some of the accuracy, or it has impacted the accuracy negatively in most of our tests. We have an alternative system that we will talk about later. Additionally, the dataset is proprietary. This is a major problem because if you can't have the dataset, then you cannot repeat the research, therefore you cannot validate the research. And the secondary problem with the dataset is the fact that the way that they balance the dataset, it's uneven, as you can tell. 32,000 benign executables, give or take, and 59,000 malicious. The way they balance it is they take benign executables and cut them in half, doubling the amount of benign executables that they have. It's not a very good method. We'll talk about it in more detail a little later. But we can't use this in an operational sense. Definitely would work in a lab, but not in the real world. So, issues with similar works. Whenever a cybersecurity engineer hears the phrase machine learning, their eyes roll out of their sockets and they immediately go blind. The reason for this is because the datasets are often not published, the code is not published, nor are any techniques for recreating the 2 published. And that makes the research unrepeatable and unverifiable and basically useless in the field because you can't, there's nothing really to run. We aim to do the opposite. We're currently on track to release the software in around 2 months, give or take, and we are working on releasing the dataset as well. More details on that later. So considering that the Intel and Microsoft dataset is proprietary, how do we recreate a similar dataset? We mainly relied on VirusShare for a training dataset. VirusShare is a repository made by Corvus Forensics, a New York DFIR firm. As of the time of writing, which is around a month ago, there were 38 million samples. I'm sure there's a whole lot more now. And in our case, we specifically downloaded torrent files 380 inclusive to 389. We pulled all the Windows x86-32 malware less than 5 megabytes in size. We identified the file type with the GNU's file command, so we just used a magic bytes to do that. And then we randomly selected 10,000 and 15,000 samples using GNU's shove command. For a testing dataset, an additional testing dataset, we used APT-Malware, which is a GitHub repo anonymously uploaded. We do trust the whole point of that repo is it contains malware written allegedly by 5 different nation states. We do trust that repo because each hash in each malware sample has a hash associated with a threat intelligence report, either written by a corporate intelligence firm or written by an antivirus company. So because there is that validation from third parties of those specific samples, we assume that the samples are true and accurate. For our benign-ware, we collected it from 3 main sources. The first source is Windows 10. We simply installed it in a VM about 6 months back or so, or maybe 9. And then we mounted that virtual disk in a Linux VM, and we pulled the exe and DLL files out. We did the same thing with Windows Server 2019 around the same time, except we selected all the services, removing any conflicting ones, and we mounted that virtual disk and pulled the executables out. Then we installed Sigwin32, and we selected every single program besides source code packages, and then we mounted those in a Linux VM and pulled the files out. There's 2 small caveats with this process. If you're mixing and matching file systems as you're copying files, do understand that Windows is case insensitive, while Linux usually is case sensitive. So be careful when copying files from one directory to another and avoid overwriting files. Disabling Clobber will help you with that. Do use fdupes or equivalent to identify duplicates, because you will have a lot of duplicates between Windows and Windows 10 and Windows Server. So it's important to identify those and remove them and not have them in your training data set. So as a summary, we have 2 major data sets. We have 15K, which is the x86-32 dataset for Windows, and we have 10K, which is also an x86-32 Windows dataset. Both of these contain 2 classes called malware and benign-ware. So when I say 10K, what I mean is 10K malware, 10K benign-ware for a combination of 20,000 samples. Compared to Intel, the largest dataset we have is 15,000 for both classes, while they have around 60,000, give or take. For us, the issue is the benign-ware is the bottleneck. We can't go higher because at most we had around 15,000 benign samples, and creating a benign data set is very difficult. We will talk a little more about what we think the open source community should do we'll talk a little more about that in the end. But that's really the big bottleneck. There are many data sets for malware binaries, but there's very few for benign ones. The imbalance in Intel's and Microsoft's data set, the way they fixed it is, again, they cut binaries in half and then converted them to images. Not a very good approach, because a binary could have, for example, a very large icon. So when you cut it in half, the second half will just be the icon file, and then the code, the variables, the logic is going to be in a different file entirely. Or you could have a situation where the code, variables, and logic and everything else is now cut literally in half. So ignoring the PE headers and other parts of the PE file. This means that the machine learning model could simply assume, not that it's a person, but it could think to itself, things that are malicious are the full binary, and things that have been cut in half is benign, and if I see nothing that's been cut in half, nothing on this machine is benign. So that's not a good approach to use out in the field. It's very lab limited. I'm sure the results work in a lab just fine, but again, we want an approach that you can repeat and recreate such that you can apply it to the real world. So now that we acquired the benign-ware, how do we convert it into an image? The Intel approach is as such. You take the binary, you convert it to a one-dimensional pixel stream. The null byte is black, the 255 is white, everything else is a shade of gray in between. Based on the pixel file size, which we assume, the paper isn't very specific, but we assume means kilobytes. You take it and convert it to a 2D image using the table on the right. So, for example, if the file size is between, the pixel file size, quote unquote, is between 10 and 30 kilobytes, then the width of the image is 64 pixels. Then the rest of the file will determine the height. So in the end, you get a rectangle. You convert the binary into a one-dimensional stream, you make that into a rectangle, and the last step is you make it into a square of size 299 by 299 or 224 by 224, depending on what your model wants. And you either use a nearest neighbor algorithm or bilinear interpolation. They didn't specify which algorithm worked best, so to emulate their work, we simply stuck with nearest neighbor because visually speaking, just looking at the images, nearest neighbor makes less images, and we assumed that that would make that would improve the results rather than having a slightly blurrier image. Our process is slightly different. Instead of using that table, we completely ignore the table, and we just take the square root of the number of pixels that we have, and we make that the width and height. So in the end, we have or in the middle of the second step, we have basically a square, right? And then we take that square and we scale it down using the nearest neighbor algorithm to 299 by 299. This method on multiple tests provided better results than the Intel Microsoft approach, so we recommend this step to be repeated should you decide to recreate the research. So on the left, you see two images with no black border around them. Those are images that were larger than 299 by 299 and had to be scaled down. The two images on the right are images that were smaller than 299 by 299. In those cases, we simply filled the background with black.
Okay, so now that we've talked about collection and pre-processing our data, let's get into the model experiments section. So this is that looping process in the ML overview flowchart. So machine learning is kind of an optimization problem. You have a bunch of different variables and you're trying to fine-tune them to try to figure out what works best. So that's what we're going to walk you through. Note too that training a neural net is non-deterministic, like I said before. So to counter this, for each model experiment we're running, we're actually training and evaluating 10 models and then taking the average of the metrics to try to reduce randomness. And our data set split is 60-20-20 train validation test. So here's a list of all the variables we're going to try to mess with. For model we're transferring width, we're going to use 2 resnets and 3 dense nets, and the primary difference between resnets and dense nets is that dense nets are more interconnected between the different layers. In terms of data set, Henry already mentioned this, we have a 10K and a 15K data set just to see if adding extra data helps. And then we have 2 variables, unfreeze bottom 10 and fine tune all layers, and both of these have to do with if these are turned on, then that means we're training more of the original model. And so if we have these on, that means that theoretically it should be more accurate because we're training more of the original model to our data set. However, this may lead to overfitting, which is when you fit too precisely to your specific data. And it also definitely takes longer to train. The last variable we're working with is the image conversion method. So either Intel's table method or our square method. So here are the 10K dataset results. Note that these aren't the conclusions. This is just the raw data from our experiment and optimization process. And the number you should care about is in this outlined row. So I'm going to point out a couple variables that matter. We found that, so this outlined row is the highest accuracy of all the rows for 10K. We found that the square image conversion method worked best, and transferring from densenet to a 1 worked best. We got an accuracy of about 96.4% here. These are the 15K dataset results. So again, this outlined row is the highest accuracy. Note again, too, that square image conversion method worked the best, and densenet to a 1 worked the best. And we got about 96.5% accuracy here. I'd also like to point out that resnets in general do worse. And like I said before, this is probably because dense nets are more interconnected between the layers.
So now I'll talk about our test data set, APT-Malware. So let me kind of walk you through the chart here. There's a lot of information to take in. So each column describes each APT. So these are the results for APT 1, APT 10, 19, and so on. The row describes the exact experiment. So this chart only shows the Intel image conversion model, as you can tell, and we have all the other variables here. Underneath each column, you have an average and a standard deviation, so you could really see how different the variable, the accuracy is between the different models. We'll quick glance here. Where it says average APT accuracy, that's per row, meaning for Intel image conversion with data set of 10K, not unfreezing the bottom 10 layers and not fine-tuning all layers using ResNet 50, we have an accuracy of 84.98% for all of these combined. So I'd like to direct your attention to this orange column called energetic bear. This specific APT in this dataset contains malware called Havex, which is a remote access Trojan that targets ICS systems, more specifically their OPC protocol. This is what Rob Lee would call stage 2 malware that actually attacks the ICS SCADA environment rather than the IT infrastructure around it. We hypothesized that it does so horribly in our tests because we don't have that kind of data set in our training data set. It's a very rare type of malware. So because we haven't trained on it, it doesn't do so well, and because it's so much different than ordinary malware. However, if we switch to the square image conversion method, you can see that all around the board, the accuracy has increased. There's a whole lot more green and a whole lot less white. And you can also tell that the DenseNet 201 on average does generally better than the other methods here. So now that we kind of went over our results, let's see if we can analyze them. We are the best accuracy we got training on the initial data set, the 10K, 15K data set. Really, the best we could get is 96.5%. So why isn't it any better? So let's take a look at the file size distribution. The file size distribution describes the distribution of file sizes of the original binaries, benignware on the left here, and on the right the malware, before they were converted to images. So benignware executables tend to start off anywhere between 0 to 100 kilobytes. There's over 5,600 samples of that. And they very quickly but smoothly taper off to single digits anywhere beyond 3,400 kilobytes. For malware, it's slightly different. We still start off high, exactly 5,000 samples. This is the 10K data set, by the way, but exactly 5,000 samples of malware between 0 and 100 kilobytes. But it kind of drops down, and there's a bit of a hump here, drops down again, a larger hump, and over here we have double digits in terms of the amount of samples we have for larger malware. The same exact story repeats itself in the 15K data set. So we hypothesized that this imbalance in the data set could cause the accuracy to be lower, simply because machine learning models do best when the data sets are exactly well balanced, meaning that there's an equivalent amount for one class as there is for all the other classes in the data set. And in this case, there's that imbalance in the file sizes. There's just not enough samples to really go on, especially if there's 1 or 2 benign samples of a given size versus 20 of malware. So the next thing we wanted to take a look at is what's in our data set. What are we even training with? So to do so, what we did is for the 10K data set, we simply sent the hash of that data set to the VirusShare API. The VirusShare API saves the virus total results when the malware was first introduced into the repository. So this isn't the actual virus total results where you can repeat the scans and get the new scans and so on. And the reason why we're not doing that is because that costs money and VirusShare does not cost money. Most malware is categorized as generic malware. So anything like potentially unwanted program, generic, Trojan, or just the word malware. Some are given numeric or otherwise, non-descriptive identifiers. We categorize all of those as generic. Some more specific categories exist also. So if we want to graph this information, we have to come up with a few rules, and there are such. If malware is categorized using only generic categories, meaning non-generic categories don't appear per a given malware sample, we count the most common generic category. If there's a tie, we use the following precedent of PUP taking precedence over Trojans, taking precedence over generic. So meaning that if there's, for example, a malware sample with 3 hits for PUP and 3 hits for generic, PUP will only count. If a malware sample has any hit for a non-generic category, we count the most common non-generic category. So if there's 30 hits for potentially unwanted program, but one hit for spyware, then we count it as spyware. We don't count the other hits. If there's a tie in non-generics, we count all ties. So if there's a tie for spyware and ransomware, we count that as a single hit for ransomware, a single hit for spyware. So, given all those rules, this is the chart that we have. Do understand that these numbers don't all add up to 10,000 because of that double counting possibility. So, let's walk through each column. We have a lot of generic malware, around 19,000 or so. That's unfortunately the reality. We can't expect antivirus companies to meticulously identify which each and every malware sample does. We have quite a bit in the spyware category, around 2,400. Then moving on to backdoor, this will be your reverse shells, your bind shells, things like that, around 15,000 of that. Droppers are the two-stage malware. So these are things that don't have the malicious payload on them, and instead they're waiting or they have the capability to download that payload and then load it later. The next category we have is riskware. Riskware is defined slightly differently depending on the vendor, but it's anything that can pose a risk to the user that isn't strictly malicious. So this could be DRM circumvention, which I would argue provides zero risk to the user, to software that can provide a backdoor, which creates significant risk. We also have adware. This is things like that inject ads into your operating system, mainly in the browser. We have viruses and worms, which are pretty standard coin miners. Exploit code, or compiled exploits generally. Then we have rootkits, only 8 samples of that. Hack tool could be anything from DRM circumvention to a Metasploit exploit to a Metasploit shell. Those could be categorized as hack tools depending on the antivirus company. And we also have crack tool. This is explicitly DRM circumvention. From there, we also have Trojans and pups, which is common knowledge, and ransomware, around 900 samples of that. So doing this allows us to see what we're actually training with. So in the future, if you have a different distribution of different types of malware, you'll be able to see that and see what you're training with and kind of hypothesize on why your model acts the way that it does. One of the other things that you might want to do when you're working with image recognition models is take a look at your false positives and false negatives and true positives and true negatives and see if there's a visual difference between them. If there is a visual difference, so for example, for an image recognition algorithm, if you see that a lot of your false positives are because people are wearing hats or glasses or masks or they're covering their face somehow, then you can tell that, hey, maybe it's a problem because they're covering their face, right? You can visually, as a human being, you can tell why the model does not do well with certain images. You cannot do this with the data that we have. So I'm going to use my cursor here to give a few examples. Take a look at this false positive here and the true positive here. They're nearly identical. There's almost nothing visually that will discern them. Sure, this one's slightly brighter, but there are examples of true positives that are also slightly brighter, like the one here, right? Really, there's no significant visual difference between these. For some reason, this little block that looks like a TV screen turned to a dead channel looks like that, but it's still a true positive, while other ones are not, right? Even though they all basically look the same. If you look at the true negatives and false negatives, same story repeats itself. So like this image looks basically identical to this one. These images over here in this little Tetris shape look very similar to this image and this image. These images look very similar. There's not really that much of a visual difference. You can't tell that, hey, this thing has an enormous icon that's showing up, and all the benign samples that have icons in them do badly. That's not the case. There's not much of a visual difference you can tell, just by looking at images. So, evaluation and discussion. File size distribution charts. Why is the accuracy not higher? Our hypothesis is as such, because there's a mismatch between the file sizes from the benignware and the malware, because they don't exactly match, the model isn't as well trained. If we had more samples that better fitted to that, we could potentially have better accuracy. The Intel and Microsoft paper also claimed that the larger the images got and the bigger they were and the more you had to scale them down, the accuracy would measurably decrease. We did not find a pattern for that. Our cutoff was 5 megabytes. The reason why we picked that is we found that larger samples than 5 megabytes were pretty rare. We didn't want to introduce things like that. We wanted to limit our training data set. So given this cutoff, we did not find any consistent pattern showing that larger images scaled down somehow do worse or otherwise.
Yep. So we also found generally that the best performing model is independent of the data set. And so we found that DenseNet 201 performed best for both the 10K and the 15K data sets. In terms of image conversion method, we found when we hold all other variables constant, that our Square image conversion method performs better than Intel's conversion method, about 70%, in 70% of our tests. And we're working on running more tests for this. And then one of the variables we changed to try to fine tune more of the layers of the original model. We found that whenever we flip the switch, whenever we train more of the original model, we always got higher accuracy. And so we think this is because it's retraining more of the original model, so it's actually better fitted to our data set. Okay, so future work. So we sort of just picked an image compression algorithm in order to fix a variable. So one of the things we could potentially try is to use bilinear interpolation instead of nearest neighbor for image compression. Another thing we're looking at is transfer learning with other models. And there's a paper mentions something called ResNet RS we're looking into. A big project would be to create our own neural network. And we're thinking about doing this in one of two ways. We can either base it solely on malware images and then transfer learn to malware and benignware, or we could create a single class neural network. So a single class being either malware or benignware, and then use an anomaly detection method to try to detect the other either malware or benignware.
So what do we think the open source community should do? Where should they direct their efforts in this research? One is the benignware data hoarding. Really, that's the main issue. Is the bottleneck is always the benignware. It's really hard to acquire a data set of that. And the big obvious reason is you can't just legally data hoard proprietary software that's been compiled. The reason for that is there's copyright and license issues and restrictions that don't allow you to conduct unauthorized copying and distribution of those binaries. Though free and open source software that's been compiled and installed, the full final executable, hoarding that should be fine, provided you have license agreements. There are millions of malware samples for Windows, but very small amounts of benign samples, so a balanced data set is required for this methodology. Software installers are also not the same as the final executable and can't really be used here. So whenever there are large data sets of software installers, we can't use those because that doesn't represent an already installed executable that just does regular operating system or application functions. It's an installer. It has a nice GUI, it has menus. Those things aren't generally present in a lot of the other software that you would normally run in your system. So we can't just use that to cover the benignware data set that we don't have. The other argument that might come up is something like, well, I don't live in, say, I don't live in the United States. I don't live in a country that has trade agreements or similar copyright laws and policies. Can I hoard it? You might be within legal right in your area, but people from other nation states would now not legally be able to use your data set in their work. So even if there are sources to data hoard, that's not really going to be available for everybody else. So really, we should expand on our techniques to acquire it yourself, as well as other methods to create more benign data sets without falling ill of the copyright policies. One-shot learning is a new concept. It could potentially alleviate problems with data set size and should be explored, though it is relatively new. It would also be kind of cool to see if we could train on more than just two classes of benignware and malware, and instead train on malware of specific types. That way we could analyze the behavior of the software in a static manner. meaning that if we have classes of ransomware, classes of backdoors, classes of spyware, and we have the benign-ware class, we could potentially say, like, hey, we are 70% confident that this is ransomware, and we're 90% confident that this is a backdoor. That would be a lot more helpful than a binary result.
So in conclusion, using DenseNet 201 for both data sets, the highest accuracy we were able to get was about 96.5%. And unlike normal malware detection methods, we're using machine learning in images, which is pretty weird. And this allows us to skip feature engineering, so it's a lot easier to develop and to deploy. And again, the end goal for this is to provide open source repeatable research.
So the best way to reach us is using that Twitter handle. My DMs will be open, so feel free to message me. We are working on releasing the source code in Dataset using an open source license, contingent of the other licenses that we must comply with. So that's going to hopefully come in around a month or so, give or take a few weeks. We have done this before, so it's not our first rodeo, so it should be fine in terms of release. We're just we're just kind of fixing the code and putting the final touches on it. We are also going to be sharing the dataset, so feel free to do so. And when the code will be available, I'll want to announce it on Twitter. But two, if you don't want to, look at that, we will make the code available at that link below. Again, using an open source license. And the goal of that is to also have it such that when you don't just have the code, you also have the models already made, so you can download the models and actually use them. And that concludes our presentation. Please let us know if you have any questions, and thank you for listening.
All right. Hey, welcome everyone. This is the Q&A session for our static detection of novel malware talk. We've got the authors here with us, and we're going to go through and just discuss a little bit about more about what they brought. And personally, I'm really excited about this talk. What I love about this most of all is your attention to operationalization and like real world results here, right? The base approach, supervised learning, sort of a basic image classification model is fairly, vanilla established machine learning, but all the magic here is in how diligent you folks have been with your data sets, using full binaries, using publicly accessible training, testing data, or at least data that you're trying to get that way, and trying to get a better balance of malign to benign samples, your willingness to work towards producing that publicly in a way that will provide reproducibility. So, I mean, like that, what would you say is like your biggest wish for all this work that you've been doing? Like, what would you like to see it accomplish?
So, best case scenario, organizations start, specifically I want, the attention of closed source entities that make antivirus software to do two things. One is to consider this method, right? Because they do have better data sets than we do. They have more researchers than we do, probably better researchers than us, right? So I want them to potentially comment. Likely not going to happen, but I'd want at least a white paper kind of discussing the topic. I understand that Intel and Microsoft kind of went over it. I wanted kind of a look at our specific process and see if there's any issues with that, because obviously having a kind of a well-funded team of people like a corporation discuss that with the open source community will help us overall, right? Help us help you, essentially.
Sure.
That's one. Two is really providing sorry, let me pull back. Lots of closed source antivirus companies do use machine learning, but the binaries are not publicly available. I understand that for benign-ware, right? Because you can't exactly violate copyright and licensing to then publish stuff. But at least the methodology for acquiring that data will definitely be helpful.
Yeah, you can't give us the data, tell us what you did to gather it so we could potentially go try and make those same arrangements ourselves with those same entities. Yeah, all right, fair enough.
Correct. From the open source side, would love the same exact thing. There's data hoarding communities, there's, the DEF CON equivalent village that Dark Tangent runs. I forget the name now, but it's the data duplication village, right? So there is a community in the open source arena that does data hoarding. So while technically speaking, can't really share benign samples, but at least sharing the methodology or speaking with kind of that community and opening up the conversation there would help us acquire more samples to train with. And lastly, really I'm hoping that, we kind of called out some names here and there. I'm hoping we'll get the attention to try and make research this exact way, right? To try and make it such that it's repeatable, to try and make it very operational, or at least focus on that side. There's many papers by universities, corporations, white papers, similar to us, FFRDCs doing research on that kind of thing. But I'm hoping that instead of it being a vague overview of what was done, instead it's very detailed, such that we can use it in an operational sense.
Yeah, no, it very much is refreshing. When we got this proposal, I mean, just the focus on these sorts of aspects is really what made it stand out from a lot of. I see a lot of sort of snake oil machine learning, stuff come into all the conferences that I'm on the committees for, and I really like the ones like this where it's like, no, let's try and concretely solve a problem and then like show what we're doing rather than just sort of say, trust us, it's all working behind the scenes. So what, if I understand, you're working on getting your results and your data sets to the point where you can release them for folks who've seen this talk and, be able to play with this themselves. What sort of license will you be releasing this stuff under, and how can the community, best give back and help you if they wanted?
So we haven't decided on that yet, but this is what I'm going to push for, and it's likely going to be this way. Hopefully a license such as MIT public, the MIT license or the BSD2 clause. Essentially, all I want is, in case somebody does the research, they link back. I don't mind it being commercialized. I don't mind it being made closed source, and a GPL has a purpose, right? And that's for Linux and operating systems, that's great. But for our research, I don't believe the open source community can match corporate antivirus. So there needs to be a way for corporations to make closed source versions. So that's the intent. In terms of the data set, malware, we can just share it, right? I'm hoping to go for a similar license. There's different licenses for data sets. So I'm hoping to go for something similar where just attribute us if you use the license. For the benign-ware, we'll have to see. Sigwin binaries could be GPL, right? Which could prevent us from publishing the model file themselves, right? So you might have to recreate the models, which would be problematic, but we'd have to speak to our lawyers to see what the situation is with that. But the hope is you'd have several files. One, tools and little scripts I wrote to help you pull data and verify whether something is an executable or not, as you install stuff. The tools to convert images, both the Intel method and our method, so that you can compare and contrast. And then hopefully a Docker file where you can just run it, create an image, and then that image would then be used for you to just give it a directory, and given that directory, you'll recursively search through all of it, find binaries, and give you like results. Those are the three core things that we're however many I listed, the core things that we're going to be looking at for the public release.
Great. So Emily, like what sort of same question, if you could wave your wand, and make some result come out of this, like or get some alternately get some access to something you don't have already, what would that look like? Are you any wish list or on either of those topics for you?
It's a big question. I have to say, first of all, I think it'd be really helpful for a lot of senior machine learning developers to take a look at this. Because I'm very very early career, so sure. I feel like I'm probably missing a couple maybe obvious things. So I think having a more experienced eye take a glance at this entire project would be useful, and we're working on getting a couple people within the company to do that. But I do think researchers with a broad range of backgrounds, so from other companies, would be super useful. Okay.
Really, I want to add to that. There's machine learning engineers who've never dealt with this problem. There's cybersecurity engineers like me who have no machine learning background and can't code this. really there's that niche that exists of both of those interconnected. And again, those generally exist at
the unicorns,
corporations. Yes. Right. The unicorns, exactly. Try and hire one for a reasonable price and let me know how that goes. But having corporations comment on this would definitely help.
Excellent. So then basically we're looking for anybody out there who's got a line into one of these groups to step up with a contact. Kick your link to them and see what they think when they kick the tires. Awesome. Okay. So then I guess one of the interesting things, you talked a little bit about some of the improvements that you made in like image processing and so forth on this. Is there like, do you feel pretty good about that? I mean, it's kind of amazing to me that compared to companies like Intel and Microsoft, for instance, you feel like you were able to get an improved process on that portion of this this mechanism. What do you think is the reason behind that, or what do you think other folks who are looking to do this kind of work could learn from what you were able to achieve there?
I think, first of all, it'd be very interesting to actually talk with the people who wrote that paper, because I am curious like how they came up with that, because it seems to me less obvious than just making it into a square. But Henry and I have talked about this, and we have no idea how they came up with that.
Right. Yeah. Generally, people have good reasons for the things they do. And it is always anytime it seems like it's glaringly, they missed something glaringly obvious. You got to wonder what data they have that you don't, or what they're keying off of that you aren't. How are their goals different from yours? Yeah, totally.
So something to add to that is, I believe they cited one paper that may have mentioned that that's the method that they use, but the actual reason why isn't exactly disclosed. I don't think they. Well, I don't want to speculate, but it could also be that their data set just works better with that methodology. Again. Sure. We have no idea to verify that. So, yeah.
So, I mean, I guess it's kind of an insurmountable problem other than, absent, voluntary collaboration and publishing from, these kinds of closed source companies operating in this space. I mean, there really isn't much way you can check a closed source, malware product or virus or something like that to find out how they're getting the results they're getting, or what data they're using, or how they got that data. And so it's kind of endemic to the space. Hopefully you guys can move the needle on that a little bit. I really appreciate everything you're doing here. So, if you want to pitch, I think you listed in the talk the ways that people can get a hold of you. Anything else you'd like to say in closing before we sign off here for today?
Yeah. So at Mehmetic Henry on Twitter, you should be able to reach me. My DMs are again open. And then on GitHub, the Aerospace Corporation, you should be able to see that, and we'll have it listed there as a project. So I'd say in terms of verifying, you mentioned the topic of verifying anti-malware, and that's really difficult because if malware is known, most antiviruses will have the hash listed in the database, so that's how they're going to detect it, right? It's the easiest method. I wish there was a way to convince those companies to do demos of their anti-malware by not using those pre-known hashes. So take your machine learning data set, maybe remove some of the APT stuff, remove Stuxnet from it, remove other APT samples, and maybe some other Mirai, however you pronounce it, other malware samples. Take them out of your training data set, train with other stuff, and let us evaluate it in an open source manner, right?
Use them for you,
yeah, because if you don't do that, then you are basically trusting the corporation and their heritage rather than trusting the technical capability of the tool. So I doubt I can, convince the corporations to do that, but that is the hope.
And to be clear, the trust is a funny thing. There's certainly reputational trust is a valid trust model, right? But yeah, it's nice when you can trust but verify, as the saying runs.
Correct.
Awesome.
Very Cold War saying.
Dato rich. All right.
Yes.
Well, I really appreciate your time, both of you, and look forward to hearing more about this when you get the rest of the data published.
Awesome. Thank you so much for having us. Great conference.
Yeah, thank you.